what we can learn indeed from having an explicit example of a holographic system. And I'll assume indeed for now that this SYK model indeed is going to be dual to a theory that indeed captures a higher dimensional. Yep. Yeah, okay, good. So this is, of course, a 1D quantum mechanics, and this is 2D gravity, known as, let's call it, put the gravity up here. And of course, the reason for why this is potentially interesting is that this gravity theory, in fact, has a black hole solution in it. I'm not going to, I think, write it down explicitly. You can essentially think about JT gravity as the dimensional reduction of the three-dimensional gravity theory, and we've seen already that there's a black hole in the three-dimensional gravity theory, and by dimensionally reducing, indeed there is this two-dimensional black hole space-time. And indeed there should be a dictionary between the two. And the fact that this is a quantum mechanical system allows us to use actual quantum calculations to learn things about entropy and other things. Now, again, this is a way of doing computations. In the end, we want to learn new things. And again, black holes, as we know, indeed have given us many puzzles. And I'll be honest, if indeed we start talking about the quantum mechanics of black holes, there are all kinds of questions that go through my mind in the sense that, well, how would we even imagine doing quantum mechanics with a black hole? Because it's a big system. Why would we even want to apply quantum mechanics to it? On this side of the story, of course, we do know that we do want to do quantum mechanics. That was one of my principles. But indeed, Hawking famously, again, when he posed the information, the black hole information problem, indeed was already building this tension between what we know about black holes and quantum information. And basically, his version of the information paradox, I can very quickly summarize it, is this picture where if this is the black hole horizon, then often how it's actually explained in the more popular literature is to say, hey, if there's quantum mechanics, then particles and antiparticles can pair create. And that happens in a fluctuating way because of, again, quantum mechanics. But they indeed re-annihilate typically. And then there is this intuitive picture that near a black hole horizon, if there's one of these pair creations taking place, that there's a Hawking particle coming out. And it has a partner which is going in. And those two combined must have the vacuum, the quantum numbers of the vacuum, which means that any information that sits in here in some sense has to be indeed entangled with the information here, because if you can only have the quantum numbers of the vacuum, if you basically cancel out whatever property this has, so if this has spin up, that one needs to have spin down, and therefore this is in an entangled state. However, the puzzle is, of course, if this thing goes far away, it will extract energy from the black hole. If we believe indeed this formula that the entropy is the area over 4 times g Newton, it will reduce the area of the black hole by this process, and therefore the entropy should decrease, and therefore eventually this Hawking particle needs to extract information. Now, in my mind, this is actually still the best version of the information paradox. And if you think about it carefully, then this doesn't care about whether the black hole is old or new, or basically it's a question about quantum information, that if the black hole has a certain amount of quantum information, it needs to kind of be able to leak out the quantum information step by step. So if you ask me, do islands or replica wormholes solve the information paradox? My answer would probably be no. And I hope that that's a little bit of a lesson for you. Generally, I would say if I have one piece of advice, don't believe anything that you hear people tell you when they're in front of this blackboard. Verify it independently, and don't assume it based on us telling you things. Form your own opinion. I can tell you my opinions, and then you see whether you want to share those or not. So, so what I'm going to do is I'm going to basically study this system. There's Jan. People will explain later why we're laughing. I didn't make any jokes. I'm just said that they shouldn't believe anything that people in front of the blackboard are telling them. So, so any case, so I'm going to do this thought experiment basically in the SYK model. Because the SYK model indeed is a quantum mechanical description of a thing that we believe is a black hole. And I'm going to ask, okay, can I actually extract quantum information through a Hawking process in the SYK model? And it should be possible to do it because this is how quantum mechanics works. Indeed, if you reduce the entropy of a system, you should be able to extract information from it. And then the other question that might pop up then, and this is sort of coming back to the end of also Jan's lecture, is that, okay, maybe I can assume that unitarity is satisfied, but then indeed the firewall version of the paradox, which is just the inverse of the paradox of Hawking, where Hawking would say, hey, I know that this thing has to be in this correlated state, or in this entangled state. Therefore, there's no way for it to extract information. And then Hawking would say, hey, since I know that the horizon is smooth, it cannot extract information because it is entangled with this thing. And if something is entangled with the partner, this thing cannot carry away information because the combination is in a unique state. Eventually, this particle has to be entangled with whatever quantum information, or at least it needs to be extracting the quantum information of the black hole. And so Hawking would say no here. The people that introduced the firewall paradox, AMPS, they would say, hey, let's assume that information is coming out, and then this thing cannot be true. So it's the same tension, but you just resolve sort of you reverse the prejudice that you have. So the question is, can you have both this smoothness here and still be able to extract the information? So I'm going to give you a toy model of how this is going to work. And that toy model will be the SYK model. So the SYK model will have, again, a Hilbert space. I told you it had a specific Hilbert space with a given dimension, 2 to the power n over 2. Another thing that it has operators. And we've talked many times about, again, this spectrum. There's the heavy spectrum, there's the light spectrum, and in the SYK, indeed, I can write down operators that are simple operators, and the simplest one are precisely, perhaps, I don't know, maybe something that is quadratic, or maybe even just the Majorana fermions themselves. This is a light operator. But then if you indeed go to a highly excited state in the SYK model, let's call that heavy states, indeed, they have an entropy, and again, that entropy is sort of this level density over here, and the heavy state indeed has the entropy, and you can verify that that entropy indeed is the entropy of the black hole. Okay. Now, so I'll do. So the way I'm going to do this thought experiment, and let me just erase this so that I have a bit more time space on this side. The way I'm going to do this thought experiment is indeed to start out indeed with a situation that is a black hole, and then I'll take the same situation as that Jan had, where I have some state psi, and I'm going to write that indeed as some superposition with some amplitudes of something with a state with energy E, and all these energies EI are very closely to some given energy, which I'll call E, in a small energy window. So this is a microcanonical state, and I claim that if this thing is somewhere in this spectrum, I should be able to interpret this indeed as a black hole. And indeed, what we're going to be doing is we're going to take expectation values in this state. So if I have a few light operators, and I take that expectation value, I'm going to compare at least these expectation values, and there are indeed situations where these expectation values are going to be very closely identified, or at least equal to the same light operators. But then in a thermal ensemble, and the difference between the two, the microcanonical and the canonical ensemble, again, is suppressed in terms of these powers of e to the minus s over 2, at least in the appropriate class of simple operators. And then this beta, which has let me give it a sub-index E, the relationship between this beta and that E, the way to obtain that is to say, hey, let's compute this thing first, which is trace e to the minus beta E of H. And then the requirement is that if I take this thing here, I should find minus E, and this equation will determine for me what the relationship is between E and beta. And I should also mention another relation, which is also true, is that if I would know the entropy, again, where the entropy is indeed the spectral density of the theory of the quantum mechanics, then indeed you have the first law of thermodynamics that basically says that if I differentiate this with respect to temperature, to energy, I got beta E. Thank you. I always got that reversed. It's 1 over the temperature, and it's beta. So I have these relations. Now, let's go and think a little bit more about these kind of observables. So e to the minus beta h is a time evolution operator, but it evolves in terms of Euclidean time. And taking the trace implies periodicity in Euclidean time. So I can represent this expectation value by means of a path integral where I integrate the Hamiltonian, or at least the path integral of the SYK model, over indeed a Euclidean circle with periodicity beta E. And then indeed I'm going to indicate an arbitrary starting point of my Euclidean time. And then let's do it this way. If I go this way here, and then here I'm at beta over 2. Here is beta over 4. Sitting down here. Here is, I guess, 3 beta over 4. And then I come back to beta here, and that's my periodicity. And so this is just a way of representing this thing in the quantum mechanics. And now let me indeed sort of make a slight jump. Although in using this G sigma formulation that I derived from the SYK model earlier on, it turns out that indeed in a specific limit of this G sigma theory, you can indeed reduce the G sigma variables to the variables that you might be able to identify with the JT gravity. But let me just, for now, indeed make the assumption that I can have this dictionary. And then basically the holographic dictionary tells me that this same partition function or this particular expectation value can then be indeed computed by doing the JT gravity computation, but now indeed on a two-dimensional space-time or two-dimensional Euclidean space-time that fills up this particular thermal circle. So the thermal circle becomes a thermal disk. Okay? And the claim is that this is a representation of the Euclidean black hole space-time. And in one of the homework exercises, I actually asked you to do the following. I wrote down a Euclidean black hole solution. And suppose that here we just insert an operator at this moment here. I'll call this one tau. I may have sort of, you know what, let me call this thing, because I can also basically decide to go this way. Let's this be positive tau. This is beta over 2. This is negative tau. I'll go like that. And they meet at beta plus or minus beta over 2. I think that's an equally good way of representing things. Then let me put the point minus tau here. Suppose I act with a light operator at those 2 points. The idea is that that light operator will create a particle in the bulk, and it will have to propagate basically from this side to that side. Let me erase this thing here. So it will propagate from tau to minus tau. And since the SYK model actually is to pretty good accuracy a conformal field theory in 1 dimensions, indeed, if I compute this particular expectation value, where this phi, actually I should maybe have called this thing phi, let's call this thing phi, is my light operator. I can have 2 light operators, one that's here and one that's there, and there's a particle sitting here in the middle that has a certain mass, and that mass is related to the conformal dimension of this particular field phi. Then I claim that if you do the calculation, indeed, in the SYK model, you get indeed this 2-point function, which actually Ian also essentially wrote earlier, tau here. and this whole thing to the power, let me call that the conformal dimension h, 2h. So it's indeed this thermal expression, because indeed if beta is very large, which is low temperature, then this just becomes 1 over 2 tau, and this is just a simple scaling. If it is beta is finite, then basically the periodicity of this thing is again indicating that this is finite temperature. And I claim that this is the answer, indeed, of having a 2-point function in a 1D CFT. It's also the answer that you would have found if you compute the boundary-to-boundary propagator between these 2 points. So this is the boundary to... Sorry? Yeah, so this is indeed reliable in this regime where the where you're in the conformal regime. But actually, it turns out that even in the if you take into account the Schwarzschild quantum mechanics, so this is an expression also for the 2-point function in Schwarzschild quantum mechanics, indeed at low temperature. Yeah, let me see if I can. That's a good question. Indeed, if you draw this 2-point function, and you draw it indeed as a function of tau, then indeed this thing behaves like so. Yeah. And it blows up at tau equals 0. And it's true that there is actually a UV cutoff, basically where this thing in the end actually turns, so it doesn't become infinite. And the reason for that is actually if I put this thing right on top of each other, then I have to compute psi times itself at the same point, since psi squared is equal to 1, which is what the equation for the Majorana fermion is. I know actually the value of this 2-point function when the two things are sitting on top of each other. So this is like a UV regulator of the whole thing. So there's a certain scale where this thing turns around, and at the moment I don't know at the top of the head of how to parameterize it in the. But nonetheless, at least there's a large regime over here. Again, this is the tau variable, and this is then 0, and this is beta over 2, where this thing is well behaved. Okay. Now, as Jan also emphasized, this phi, it's an operator in a CFT, or in this case in the SYK model, and it's actually useful to think about phi in terms of its matrix elements. For example, between energy eigenstates, so later in a moment I'm going to be introducing indeed a matrix notation for this phi in the same way as Jan was sort of decomposing his thermal 2-point function. And it's useful indeed to think about this situation in terms of energy eigenstates. So let me actually still write down the same formula that Jan wrote down. But now I'm going to do it in this setting. So Do you know what? I'm going to make my life easy a little bit. I'm going to, because in the end it doesn't matter that much that I have this sum over C i's. I'm just going to pick one of these things. I'm just going to take the actual energy eigenstate just to reduce my writing. In that case, I can do the following. Just to illustrate briefly what the structure of this is, and then I can actually extract the tau dependence by in the way Jan also did, by doing this, and then explicitly writing down e to the minus tau e I minus e, and there's actually a factor of 2 here. In terms of the picture over here, the way you have to think about it is that I'm inserting an operator on here. So this is actually why the operator, where the state I sits, E sits. So E is the energy of the state I'm introducing here. The place where I put 0 is the place where I can insert a complete set of states. So if I think about this state here, phi acting on psi, it's the state that I'm preparing by doing this part of the integral. So maybe I should briefly draw that picture. Phi tau acting on E. I'm representing it like this. I put E here, and I put phi of tau here. Tau here. So the state, which is the in state, describes the lower half. So that's the cat state. The brass state describes the upper half. Okay. The following is actually a useful picture. So if I draw the black hole space-time, if I draw a Penrose diagram, I would draw it like that. So this is Lorentzian. And then real time goes up. Actually, it goes down here to some extent and goes up here. And this is here is the horizon, and we have the interior of the black hole. What I've been drawing here is the Euclidean space-time. Now, what do these two space-times have to do with each other? And the way this works is that, as I said, I could actually think about this as cutting this thing into two halves, where the lower half is actually the path integral that prepares the state. So if I view this as a state, that was prepared by a Euclidean path integral. But now I'm going to take this state and I'm just going to let it evolve in real time. So at this point, after preparing the state, what I could do is I could actually let time evolve upward. And indeed, what I'm going to do is I'm going to identify this horizontal line here with this horizontal line here. And I'm going to glue this upper part of this diagram onto the lower part of this diagram. So what this describes is basically the quantum state at time t equals 0 of a black hole. And then indeed this point that sits in the middle becomes the horizon. The point that sits here in the middle indeed is the horizon of the Euclidean black hole. But here indeed it gets identified with the location of the horizon of the Minkowski black hole. So that's one way of at least thinking about this situation, is that the state that I was preparing in the lower half, indeed, if I don't act with any operators here, the state described by this path integral without any operators is indeed the thermal field double state that Jan described. This is the TFD state, which you can kind of identify with e to the minus beta over 2 times the Hamiltonian. But then you have to do this funny thing where you switch the brass and the cats to write it as an entangled state. So that's the idea. And indeed, if I start acting with operators along here, I'm acting with operators along this boundary. Okay? Are there questions about this picture? At least it should relate to some of the things that Jan has talked about. So basically, this is partly, yeah, go ahead.
So in this part, what we said is that this is an SYK calculation that, right? And now what we are trying to do is
interpret the SYK calculation.
And so maybe my question is, when you draw these both Euclidean and Lorentzian in one diagram, how should we interpret what the axis is and what means how?
Yeah, so let me try to motivate at least why I'm drawing those diagrams on the right-hand side. So what I want to do is I want to be able to consider a state where I have indeed not just the black hole, but I want to start probing the black hole indeed by having particles in there. So indeed I may want to have, say, a particle that moves here. And suppose that the particle wants to be at that particular location at time t equals 0. What I can do is, okay, my question is, what should I do in this site in the preparation of the state to put the particle there?
I see.
And then I say, okay, what I do is I'm going to act with an operator phi down here, which indeed will create kind of an excitation. And this equation motivates that I should be interpreting this thing as a particle with a certain mass. And since it sits here at this location at this particular slice, basically I'm going to be interpreting this particular state as a state that at this particular moment in time has a particle sitting there. Okay? And the thing that you see happening then is because basically the anchor points of this, where I act with that state, I can start moving, and I can move this point all the way up here. So depending on whether tau is bigger or smaller than beta over 4, I either will be creating the particle on the right of that point, or if I move through here, I will be creating the particle on this side. Right? Because again, the tau parameter will just move me this way. So indeed, in that sense, a particle that's being created here, indeed, will then propagate in this direction here. So let me draw that in yellow, why not? So I could have another point that I call tau tilde, and here it's minus tau tilde. And tau tilde is bigger than beta over 4. And this yellow particle actually sits inside of the black hole. And the white particle sits outside of the black hole. So that's the dictionary, at least that's suggested by holography. And last, at least on Wednesday in my first class lecture, I was indeed computing for you, if I look at this particular state, phi tau on E, and I was doing the operator product expansion calculation, I was arguing for you that if I start moving this thing closer and closer to the heavy operator, that is going to be a qualitatively new behavior. If this phi is farther away from the state, this phi will be adding energy to the system. And indeed, from the operator product expansion, you can see that you're going to add energy. But when you get closer to the operator, then indeed, because of the fact the way the scaling works, eventually this thing is going to be lowering the energy of that state. So let me again draw that then over here. So if this thing here has energy E, and I call the energy here E prime, then I will have two types of situations. In this situation, E prime is bigger than E. But I claim that in, let's do that yellow, why not? Where I do tau tilde. And here is E prime, and here's E. In this situation down here, E prime will be less than E. And indeed, because of the behavior of the OPE expansion, but you can just compute that actually in the way that was also one of the homework exercises, is to just differentiate this with respect to tau. Take the logarithm of this thing, differentiate with respect to tau. That thing is computing for you the difference in the energy between E and E prime. And that difference energy will indeed be positive in this regime, and it will go negative in that regime. And again, this should not be a surprise from the space-time perspective, because indeed, if I put a particle here, time goes backwards. Basically, here time moves forward. So a particle that I created here actually carries negative energy, and a particle that I create there carries positive energy.
So someone, maybe I'm very naive question, but this quadrant is actually not the interior of the black hole. It's actually the other, the extension of the black hole.
Okay.
Right?
Okay. Thank you. Very good.
So.
Yeah. Okay. It's true. That's a little bit of a slight confusion in some of the discussion. A good question. So indeed, if I have a Hawking particle coming out, so indeed this particle that I was drawing earlier, the Hawking particle coming out, basically it comes out here. And then the question is, where's the Hawking partner? Yeah. The Hawking partner kind of sits here. Maybe you should draw that one then in the yellow. So indeed, the correlations that Hawking is talking about that tell you that the horizon here is smooth has to do with entanglement that's between opposite sides of the horizon. And indeed, it's the interior of the black hole with the exterior. Yeah.
So, but somehow in your picture, if we take the particle interpretation of state creation, the yellow line is actually in the extension of the black hole.
Yeah, so indeed, but basically the way, at least practically, you want to think about it, is suppose that indeed I have full control over understanding what happens on this full spatial slice. And if I understand how this spatial slice extends beyond this point,
I see.
And I know that that state looks like a smooth QFT state of the low energy theory in the bulk, then the next thing I'm going to do is I'm just going to use the way I propagate QFT states forward in time. And so if I have control over this line here, I also have control over what happens in the interior. Okay. So in that respect, the mystery of what happens at this particular point is directly related to the mystery of the firewall paradox, because as soon as I don't know what happens beyond this point, I also don't know what happens beyond that line. So the potential of having a firewall along this line is equivalent to essentially the geometry breaking down on the left of that particular point.
Okay. Thanks.
Maybe a naive question, but how do we know that we're not increasing or decreasing energy by putting the right or left side? Like, how are they exactly defining it?
The energy?
Yeah. Like E prime and E, like.
So the difference between E prime and E is that and this is indeed an important question. So if I look at this particular expression, I fixed E.
Yes.
So E is in a microcanonical ensemble. So I'm fixing E.
Okay.
And I'm relating the temperature of my situation to E. And if you think carefully, indeed that's an important statement, that I'm working in a microcanonical ensemble that fixes E, because if you start computing thermodynamically what the energy is in this other region, this E prime is different from E. It will actually depend on tau. But that's because the temperature here indeed is also going to be different than there. But the way I'm doing my ensemble is by fixing the energy in this side.
Thank you.
And therefore E prime will be the thing that depends on the location. Yes. So the question is, does the calculation depend on large N? Yeah, I would think so, yes. At least, certainly the way I've been thinking about SYK, then there are going to be 1 over N corrections. So I'm cheating a little bit in the sense that some people may indeed correctly asking, well, how big is the Hilbert space? Is entropy finite or not? Because if I take strictly the large N limit, entropy is going to be infinite. And then perhaps I don't know if information is lost or not. So let me just say this. I'm just going to be taking N enormously large but finite. And then any corrections to this should be suppressed still in terms of 1 over N. Let's say this way. If I do, at least the question is the geometry smooth here or not? For now, let me try to be agnostic about it. I would say I'm only going to accept that the geometry here is not smooth if I find some funny behavior in these correlation functions. So if it turns out that if I would actually be computing this correlation function, and I would suddenly find a very odd behavior at beta over 4, then, because that's the moment where this world line will basically cross that point, semi-classically, then I would use that as an indication that the horizon is probably a funny place. Whereas if everything is very smooth when I go through that beta over 4, then I would say, hey, now I have evidence that this location here is actually nothing too special. And actually, we have found something special that happens at that value of beta over 4. Because indeed, I claim that that's precisely the moment where this E prime goes from this to that. So there is something happening there, but I claim that that's not something that necessarily makes this correlation function behave badly. It's simply the fact that this particle was moving to a region where it had positive energy to a region where it had negative energy. Now at this point, I think I can introduce the observable that I would like to study. Let me still make one comment. So I've been drawing these pictures, and let me just use this picture here. So I mentioned this already in one of the discussion sessions, but I think it's still important for me to kind of mention this. Indeed, this transition, again, between, if this is E, and E prime is smaller, and E prime sits somewhere down here, or indeed I could have the other situation. Let me actually start with that one, where E prime sits here. By the way, maybe I should label the top situation, I'll label that situation number 1. Situation number 1 is where E prime is bigger than E. Situation number 2 is where E prime is smaller than E. And therefore, this operator phi either goes from something that's smaller energy to bigger energy. And it also goes from a situation where S of E prime, the entropy at energy E, will be bigger than S of E. And I've indicated that by drawing more lines here, so the spectral density is bigger. Here, S of E prime is smaller than S of E. So at this point, indeed, the particle, when I act with phi, I'm reducing the entropy. So this is the yellow situation, I guess. Maybe I should indeed draw this thing yellow. So the phi of tau tilde is an operator that goes from a bigger Hilbert space to a smaller Hilbert space. And this is indeed a way of kind of reducing the entropy and therefore extracting some kind of quantum information from the black hole. So, because essentially, indeed, again, the Hilbert space has become smaller, and then the question is, where is all this quantum information that sits in here? Quantum information is proportional to the number of states that I could have written down. So what I'm going to do now is I'm going to basically use this intuition to do this thought experiment of Hawking. Or at least I'm doing a thought experiment that basically is going to model the Hawking evaporation process where I need to pair create a particle, a pair of particles. So what I want to create, let me draw it again in that geometry on the right. And it's actually useful to do this in this funny half Euclidean, half Lorentzian way. So what I'm going to do is I'm going to put a particle here, and the Hawking partner I'm going to put here. And this one is, yeah. Now what I could have done is I could sort of, put it here, and then initially let it sort of be created just right on top of each other, and then I just start moving one out, and this one I start moving in, okay? It turns out, okay, we'll talk about this later. So once indeed this Hawking particle has become real, it can become a particle that can start propagating like that. This particle will go this way. But there was some kind of Euclidean process, and perhaps I can either think about it perhaps as something that connects them over here. This is maybe the way Hawking would have drawn the pair creation process, where he said, hey, these particles were created, one of them escapes, the other one goes into the black hole. And indeed, since this one has negative energy, and this one has positive energy, initially they're created in a way where they don't have any total energy. But eventually, once this particle escapes to infinity, it will extract the energy from the black hole, because this particle indeed will have negative energy, okay? And now I want to start analyzing this particular situation and ask, okay, where did the quantum information go, okay? Now, to do that, what I'm going to do instead, I'm going to, indeed, I want to create this particular initial state, and the way I'm going to do that is by, indeed, acting with an operator phi tau here, and simultaneously acting with an operator phi tau tilde over here, again, where tau tilde is beta over 2 minus tau. And it turns out, indeed, that if you precisely choose this value of phi tau tilde, that the combination of these two operators will actually, indeed, not add any energy to the system. So if this energy is E, there's going to be an energy E prime here. And again, there will be energy E here. So this is my Hawking pair situation. And this particular lower half of this space-time diagram represents a state which I'll call, again, the Hawking pair state. And it will have a phi of tau tilde. Actually, that one acts second. Phi of tau tilde, and maybe you should draw that one yellow. Acting on E. This is my Hawking pair state. Let's call it a Hawking pair state. Okay. So when I say that this carries negative energy, so my interpretation is the following, is that if I take the state prepared by the lower half of this diagram, my perspective is that I'm measuring the state at this point. So here I'm measuring the state. So so this is where E is being created, phi acts on it, and this is where I'm looking at it. So this state phi tau of E will have energy E prime that I put here. So E prime is the energy of this state. Yeah, so here indeed, in this picture, since I now have two operators, I have an energy that I started with, which is this energy. This one will do something with it. And then the E prime is the energy of this particular state. So this thing will have energy E prime. And the total state, again, has energy E. Okay? Let me call this thing G of 2 tau.
Sorry, it seems like I missed a question on the chat. In Euclidean signature, horizon is a point in the RT plane. What does it mean by the yellow curve as particle inside the horizon?
So the question is indeed, the horizon is a point here, but it's a point that lives on a given time slice. And indeed, it divides up the spatial slice into an interior and an exterior. So when I mean that the yellow line is in the interior of the black hole, is that it goes through the half of the line that sits on the left of that point. Again, if I call this the horizon, it's called actually the bifurcate horizon. So even in this case, this point here is what's called the bifurcate horizon, but then indeed the light rays that emanate from the bifurcate horizon are also the actual horizon of the black hole. But in Euclidean space, there are no light rays. So in Euclidean space, it's just a point. In Lorentzian signature, it's a light cone. So that's the answer to that question. So now, what I'm going to do is basically I'm going to do thermodynamics with this particular state. And I'm going to compute for you indeed the moment where this E prime, so there are going to be again now two regimes, which is kind of perhaps a little bit surprising, is that E prime, when tau is very close to this, when the pair is very close to the horizon, it will turn out that E prime, first of all, it's actually going to be very, very random, but its expectation value will actually be bigger than E. So initially what happens is that, that this thing is what we actually would call a virtual pair. So it just sits there, and by putting it actually in the geometry, we're actually increasing the energy in the middle part of it. But eventually, when this thing is coming out, eventually there should be a point where E prime is going to be smaller than E, because indeed, if this thing in the end is going to disappear, this phi of tau, basically let's suppose I detect it in some detector, then I'm left with the situation where only the Hawking partner sits inside of the black hole, and at that point, this Hawking partner will be in this situation where the energy is less than the total, and that's when I have extracted the energy from the black hole. I'm going to indicate to you when the information actually is going to come out, and it will turn out that there's a finite location along this circle where suddenly information will be coming out. And the computation is a little bit similar to the replica Warm-up calculation, but it basically makes use of a simple observation that suppose I introduce what I may want to call the partition function of the Hawking pair. So I take this state, let me call this state psi, big psi, and I'm simply going to take the inner product of psi with itself, not normalized, I guess. So I'll compute this thing here, phi minus tau tilde, phi minus tau, phi tau, phi tau tilde, E. I claim that, again, to very good accuracy, I can write this thing in this way. As a thermal expectation value. And moreover, and this is indeed where I'm going to be using large N, I'm going to treat these phis as something that are called generalized free fields. So at large N, I'm going to assume that phi is a generalized free field. And that may seem like I'm saying one of those things, and this is one of those moments where you say, hey, should I believe him? And maybe you shouldn't. There are quite a few arguments that indeed if you do holographic, look at holographic systems, that if you take an appropriate large N limit, and you look at all the diagrams that contribute to an object like this, that those diagrams indeed involve all kinds of contributions, but then if you take the large N limit, that the wick contractions between these phis essentially are the dominant contribution, and anytime there's an interaction, that the interaction is actually suppressed by 1 over N. And I'll motivate that a little bit in a second. So what I claim is that I can start just doing free field calculations. So in a picture, this thing again, if I draw it in that circle notation, if I take this particular partition function, I'm taking the inner product between the state with two Hawking pairs, one Hawking pair, between the brass state and the cat state, and then I need to compute that correlation function. And I claim that that correlation function will indeed have two contributions. It will have Yeah, let me actually just draw it like that. Two types of wick contractions that I can do. There's the wick contraction between this point and that point, and maybe I should still draw the point yellow here, and maybe it's yellow. So this is the wick contraction between these two guys and then those two guys. That's this picture. This picture is the wick contraction between this guy and that guy, and this guy and that guy. For those of you who are paying attention, there's actually a third wick contraction that I should draw, where this guy goes all the way here, and this guy goes all the way there. And the reason I'm not drawing that particular wick contraction is because it turns out that basically the contributions of these two wick contractions can be competing with each other, and the one that dominates is the one where the length between the two is the shortest. And I claim that depending on the value of tau, one of these two things is going to be the shortest. And the one that goes diagonal is always going to be longer than the other ones. So for now, I'll ignore the ones that go diagonal, and I claim that this is sort of a good way of thinking about the wick contractions in the bulk. Each of these wick contractions is just a product of two Green's functions. So if I compute this thing, then this thing is the square of g of tau minus tau tilde squared. That's just this thing. Because this one is tau, that's tau tilde. This one is tau, this one is minus tau. So the second one is g of 2 tau squared. So this is the first one, and this is the second one. I'm just basically saying, okay, the 4-point function factorizes in, this is called large N factorization. It factorizes into 2-point functions in this case, and it's the sum of these two. Are there questions about this? This is what you would do if you would do wick contractions again in the bulk. By the way, another way of suppressing these diagonal ones is if I would make this to be the creation field that creates a particle, this annihilates the antiparticle. Then this creates the particle and this the antiparticle. And this particle to antiparticle, antiparticle to particle, no, particle to antiparticle. And then I can also have this, particle to antiparticle, particle to antiparticle, but then this one would not be a wick contraction. So that's another way of getting only these two terms.
Would that be g of 2 tau into g of 2 tau tilde instead of g 2 tau?
Yeah,
square?
but 2 tau tilde, so there's, it's actually modulo beta.
Okay.
And this thing is exactly equally long as that thing. So this 2-point function is equal to that 2-point function. The reason is that tau tilde is beta over 2 minus tau.
Oh, okay.
And this minus tau tilde indeed is minus beta of 2 plus tau, but then if I do it modulo beta, I get. So this is what you would expect.
This will probably sound very naive, but in the construction, where you are, in that Penrose diagram, so you're talking about the yellow particle going into the interior of the black hole, am I right? But isn't the interior of the black hole just the upper wedge of that,
Here.
Yeah, indeed.
Yeah.
In which sense, so like the yellow particle, once we go to the, let's say, Lorentzian part of this, of the space-time,
yeah,
isn't
so that's the same question I was asked indeed earlier. So indeed, it's a slightly subtle point. At the same time, as I was mentioning, is that I'm interested in what's happening on this particular spatial slice. And previously, perhaps we would have phrased the firewall paradox as just, or the questions that we're asking about quantum information as associated with this upper horizon, which is to some extent true. But I claim that if we analyze things on this particular slice, if we understand what happens at this point, and if I understand what the correlations are between here and there, and those are the correlations also that Jan is talking about in the thermal field double, is between these two sites. If things are smooth over here, if I understand low energy quantum field theory over here, then I can just use propagation to kind of compare what's happening here with what's happening there. But maybe what you're objecting against perhaps is that if I call this thing the Hawking partner, why am I making it go like this? And there's a certain sense in which it really is sitting on this in this side of the wedge, if I look at it from this perspective. But it really depends on what kind of Hamiltonian I'm taking when I'm going to move this thing forward in time. So I would say take the picture sort of somewhat semi-seriously with the same warning that I've been giving earlier about just taking your own judgment, that what I'm creating is a state on this slice where indeed I'm having excitation on each of these side of that particular bifurcate horizon. And I'm just going to think about this as the Hawking partner. And so a priori, indeed, I now know actually this inner product, and I'm going to think about this as indeed as a thermal partition function, and then I'm going to write down a few equations that will tell me what the value of the e's and the e primes are, and just will be able to compute those. Just in the usual way, one computes thermal expectation values. By the way, there are two ways of doing this computation. Let me still do the yeah. First, I'll do the thermal calculation. How much time do I have? 20 minutes. Okay. What is the approximation that you object most to? Okay, let me then do something else. Now I'm going to do this something else thing. I'm going to introduce a random matrix. It's called C. And it's going to be e to the minus beta over 4 times the Hamiltonian times phi. Okay. And I claim that if I define this random matrix, so this is a random matrix because phi is an operator that acts on the Hilbert space of the SYK model. And I claim that this particular object that I have written here, or this one here, I can write this one as the trace of C dagger C, C dagger C. I can plug this in here and I can write it like that. So C is the matrix of matrix elements of this particular operator. And now I'm going to evaluate that trace by summing over the energy eigenstates, by inserting a complete set of states and summing over the energy eigenstates. And then I'm going to use your words, and for once I'm going to believe you, where indeed these are random matrices. But the C and the C dagger are conjugate random matrices. And then if I'm interested in a particular matrix element of the C dagger matrix, it will be a diagonal. If it's off-diagonal, it will average out because of the phases averaging out. And the off-diagonal elements are e to the minus s over 2, the entropy of 2, so it's square root of n suppressed. And therefore, I can start to evaluate this thing in basically representing these as random matrices. And then this thing can be evaluated basically by Wick rule, by representing these matrices maybe through a Gaussian ensemble, but basically by the same statistical arguments, I can say, hey, this thing is going to be a sum of two contributions, where I either Wick contract these two with those two, or indeed I Wick contract the C dagger with this C and this, sorry, with this C, and I Wick contract those two. So the sense in which I have these two Wick contractions, I can motivate. So this is actually a large N argument. The large N is the fact that these are very large random matrices. And the approximation that I'm taking is that I can make those Wick contractions. So I can find the corrections, and the corrections are as small as you want them to be, namely e to the minus s over 2. Okay?
Maybe my concern was that if you I mean, I believe and understand the computation, but the question is whether by making these approximations, because in some sense doing this random matrix approximation is somewhat similar to a semi-classical approximation, have you not basically lost the unitarity?
No, I'm going to restore the unitarity at this point.
Because if you, somewhere in your approximation you lose unitarity ever so slightly, then you may get a wrong conclusion. So the question is whether you have, by making approximations that are well motivated, but by making tiny little approximations, whether you have sort of put the answer in to some extent.
So I'm going to give you a quantum information theoretic mechanism by which information is being extracted. You can the mechanism is going to be specific when it comes to how the quantum information can be followed. So I'm going to give you a picture to follow the quantum information. So then you can have two attitudes. Either you can say this was trivial, it's something that you already knew, or you can say it's wrong. In this case, I think you might end up being closer to the first one, where you say this is trivial, something that you may already knew. But there's going to be a new piece of information still in this whole game, is that, and this is actually partly where precisely replica wormholes and things like that play a role, is precisely when you have these random matrices, then in some cases the constructive interference happens in one channel, and then when you go to the other topology, the constructive interference is happening in another channel. And what I'm saying here is that in this case, the jump between the two channels, which is the jump between these two Wick contractions, is not determined by a page curve. It's not determined whether the black hole is old. It's not determined by any wormhole geometry. It's just going to be determined by the length of the propagator of the particle. So the elements in the story are still the same ones as that I have e to the minus s over 2 kind of off-diagonal terms in here that are constructively, in the end, still contributing. But I'm not doing anything that's e to the minus SBH, e to the minus the black hole entropy, in terms of the relative importance of these two terms. So this at least gives you some intuition. And again, let me still, since we're talking about this picture now, so here I can actually quite easily indicate now the energies that I was interested in. So if indeed there's an energy E here, there's an energy E prime here, and there's an energy E there. So let's look at it. I started with the state E here. Let's start on this side. Then there's phi of tau tilde sitting here. So E prime sits here. E sits here, E prime sits here. So in terms of this picture, E sits here, E sits there, E prime sits here, E prime sits there, E sits here, E sits here, E prime sits here. Okay. Yeah. So I'm using letter C because it's a nice letter for random matrix. It's an operator product expansion coefficient. So it's related to matrices C's that Jan and company also are talking about. If you think about the individual Hawking evaporation process, it is one of these random matrices that indeed represents the emission of a particle. You can think about it this way. But indeed, so here's the important part: is that again the E that are sitting here in the intermediate are labeling the intermediate energies, and therefore they label also what happens in these intermediate channels in this product. So E was sitting on the outside, but I replaced it briefly in terms of this trace as still an index that kind of goes around. But then E prime was sitting here, E is sitting here, and E prime is sitting here. Now, so if E prime, say, is bigger than E, then C is a matrix that goes up like this. It goes from here to there. So this dimension is smaller than that dimension. So if E prime is bigger than C, the number of indices that are common between these two matrices is bigger than the number of indices that are common between these two matrices. Because the index contraction goes here, it goes like that. So so the rule of this particular game is I'm going to keep track of where the most indices are. So if this E prime is bigger than E, this one wins. Because this wave contraction will dominate over that wave contraction, because E prime, there are more E prime indices than E indices. So let's see if it actually works out. This one is the one that happens here. So the top one is the left one here, which is when E prime is actually bigger than E. At this point, I would call the Hawking pair still virtual. And indeed, this point here is connected in the geometry with this E here. And it turns out that the entropy of this particular situation, which you can compute, is just the energy, the entropy associated with that energy E. So in this diagram, the energy of the black hole is, the entropy of the black hole is not yet changing. The pair is being created, but the black hole will have still entropy S of E. At some point, however, this distance here will become shorter than that distance there. If this distance becomes shorter, this thing will become bigger than that one. And this one will start dominating. And indeed, that's the moment where this E prime is actually less than E. Because now, indeed, this wave contraction is happening along the indices where E is bigger than E prime, and therefore E prime is less than E. Since now in this geometry, this point here is connected with the place where energy is E prime, the entropy of this particular situation is S of E prime. And indeed, you can do a replica wormhole calculation and verify that the entropy in this case is S of E prime. And since S of E prime is actually less than S of E, this is the moment where the information is going to be extracted from the black hole. So that's sort of the intuitive picture, is that what the Hawking pair is, it's sort of like a pump, meaning there's quantum information here, that's my well. I take my Hawking pair, I start pushing it into it, and then at some point, the pump will basically say, hey, this entropy can no longer go through here, it kind of has to jump over here. This is the moment actually where quantum information is going to come out. Because basically I've extracted the entropy from the black hole. So this gives you a very nice, at least in my picture, in my view, a nice semi-classical way of thinking about when entropy is being extracted. And this is sort of a mini version of the Page argument. Here entropy was going up. Actually, if you think about it, at some level this is the moment where entropy is going down. And indeed, the black hole information paradox has a mini, or at least an incremental version of it, where for each Hawking pair creation, I have to be able to tell you when the information is coming out. And this is sort of the intuitive picture. If you wish, I can do a very quick thermodynamic calculation in 2 minutes, and then I'm done. Or do you know what? Let me. I'll instead of writing down formulas, I'll just draw pictures, and I'll do instead of doing the thermodynamic calculation, which is just by taking this partition function and doing differentiations with respect to tau and extracting the energy from it. I'm going to do the replica calculation. Homework, or you can look in a paper from fall. I can do the replica calculation. So I'm going to call this thing rho, and I can want to compute the trace of rho to the n. And let me actually take this notation because it's kind of convenient. It means I have to write down this density matrix here and then take it to the nth power. But basically, if I use that C notation, what I need to compute is C, C dagger, C, C dagger, C, C dagger, C, C dagger. N times. So now, indeed, because I have rho to the power n, and rho is basically, diagrammatically, rho is this path integral that I'm doing, and if I break this thing open here, the rho is this circle with 4 insertions. So here, of course, I have 4 times n insertions. But now the circle basically effectively has become n times longer. So I have now a large circle, like so. And actually, I'm going to draw 2 versions of it. And indeed, I'm going to, so let me take n equals, I guess n equals 2 is big enough. So this is where my 8 operators sit. Here I had 4 operators, but now I do trace of rho squared. So I have 8 operators. And again, if I compute this particular quantity, and I get the sum of the two, then indeed, if I want to start computing Rayleigh entropies, this is how I should do it. And then again, I have to compute this expectation value. And I'm going to do indeed the 2 Wick contractions. So, okay, let me just do it like that. Oh, wrong one. Maybe I got my colors mixed up. Never mind. I think I want to draw these ones yellow. So energy is E here, E prime, E prime, E, E, E prime, E, E prime. Here energy is E prime, E prime, E, 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 E prime, E prime, E. Okay, so I'm now computing the second Rayleigh entropy. If I do the second Rayleigh entropy, because that's part of what the replica method tells me, indeed I'm going to get different contributions again, because I can start doing Wick contractions. Again, I can either do them this way, by doing the nearest neighbors, or indeed I can do it the other way, where I start actually with the other one, where I start with Wick contracting this with that, and then I do the ordering. A priori, by the way, you could have imagined perhaps doing Wick contractions between, so let me ask this question briefly. Why am I not Wick contracting this C with some C much farther here? Basically, it's like, if I would do that, I would actually create one of these other index contractions that, according to Hof, would be suppressed by 1 over n. Basically, the index contractions are forced on me by the trace, and therefore the nearest neighbors are the things that I want to interact, contract. So I only do nearest neighbors Wick contractions. So these are the two ones that indeed are still the two dominant ones. There are more Wick contractions, but again, they kind of are somewhat suppressed. And then the although maybe, okay, let me think about it. Then the remark again is the following, is that in the regime where this one dominates, which is precisely the same regime that I've been talking about before, the entropy that you're going to obtain is still the entropy of the original black hole, because of the fact that the horizon here sits in the entropy region S of E, and here the entropy is S of E prime. So indeed, one can actually compute this correlation function. The correlation function, this Rayleigh entropy is then the G of tau minus tau tilde to the power 2n plus G of 2 tau to the power 2n. So it's again a sum of these two things. So now I've computed the Rayleigh entropies for you, and then as again an homework exercise for yourself to go from the Rayleigh entropy to the von Neumann entropy by taking the n to 1 limit. So you should be able to write down an explicit expression for the von Neumann entropy of this particular state. And then this is how you can kind of analyze what's happening. So let me wrap up. So in some sense, I'm ending at the same point as where Jan ended up, is that there is actually a geometric way of starting to do computations in terms of the quantum properties of an underlying quantum system that indeed in this dictionary can be mapped to a geometric calculation in the gravity. The kind of quantities that we can compute are indeed these Rayleigh entropies. But every time I get an answer that I can actually represent in terms of the gravity, effectively what I've done, I've always computed something that involves something like C times C dagger. So I'm only computing the quantities that are actually constructively interfering in the multiplication of random matrices. The thing that I haven't computed for you, I don't know what this matrix C literally looks like. So I haven't given you a microphysical description literally of what's going on. I've only given you the dictionary between the microphysical description in terms of the matrix elements of the quantum system to quantities that you can associate with things like entropy that need to keep track of information. But I think, at least from a mechanistic level, I think this definitely is sort of a new perspective, at least I would say, on the question that Hawking basically started asking with the Hawking pairs. Again, of course, there are many other directions that one should be still exploring. And indeed, I would say, if you have questions, don't view those questions as something where you don't understand what we've been telling you. Those questions are going to be the next things you want to get the answer to. And that's the way in which you're going to do new things. So that's where I'm going to stop.
This is just out of curiosity. The space-time you constructed there, basically, I think a similar, if not exactly equal construction has been used to try to ask questions on boundary CFTs on a closed time contour. I think Jan has a paper on this. But is this like it's just a coincidence, or there is something profound behind this?
Yeah, so let's make a few. Yeah, we can make a few comments on this. So we also actually have been studying similar diagrams in a previous sort of work that actually preceded the replica wormhole calculation, where what we were interested in was what we call partially entangled states, where indeed what you do is you do this computation of the thermal field double by time evolving over the half thermal circle, and you insert potentially even a heavy operator. One thing I didn't talk to you too much about is that again, if you do this in SYK, the boundary actually, I've been drawing them as nice little circles. But one of the nice things of SYK is that the boundary is really kind of dynamical. It's described by the Schwarzschild derivative. And there's a very nice sort of physical picture where essentially the Schwarzschild action can be derived by considering basically a boundary that can indeed fluctuate. You map it onto the Poincaré disk. And then basically the action for this boundary trajectory will just be the area in the interior of this Poincaré disk, and that thing provides sort of an attractive force, and the length will cost an energy. So there's some balance between the length. And then what happens as soon as you start inserting these operators, basically you get back reaction, and you get funny sort of cusps in your diagram that pull the things inwards, and then these propagators that I'm drawing actually become domain walls. So it's certainly possible to already sort of have similar kind of calculations where indeed these propagators are actually kind of more like domain walls. But then indeed at that point, of course, once this thing is a domain wall, the next thing you might want to do is perhaps turn it into something that people nowadays might want to call an end of the world brane. And then you just then you remove this part, and then this basically becomes like a boundary CFT, where indeed sort of the description of when you basically your CFT has a boundary on the boundary of the ADS spacetime, and since the CFT has a boundary, something has to go through the bulk. And it's true that whatever happens in the bulk, most likely if it's some kind of brane, it should also follow the minimal area or the minimal length trajectory between insertions on the boundary. So indeed, it's true that this kind of same type of geometric situations can be considered also in these other settings. Right. Yeah.
In this setting also, something like this entropy going up and down, we've reproduced purely in the SYK model and not doing a calculation in JT gravity or anything, right? The way we described it.
Yeah, let's say it this way. There's a way of thinking about sort of the entropy going up and going down, and indeed it turns out, by the way, if you do this computation and you take that quantity and you extract the entropy from it, you're indeed going to find a thing that where initially actually the entropy seems to be going up, and then it's going to be going down. So there's kind of a mini pace curve already in this particular setting as a function of, not as a function of time, but as a function of that tau parameter. Whether or not you want to call this thing in computation in the SYK model or not is slightly a matter of taste, because if you take this philosophical diagram that I had earlier in my talk yesterday, where I had SYK here, and then, I'm sorry, I had whatever bulk theory I had over here, which I don't know what it is. SYK was sitting here. Then there was this effective low energy description, which was the Schwarzschild. Basically, these are computations that you can explicitly do in the Schwarzschild. And whether or not I interpret that as being in SYK, I don't know. It's I still have made some kind of approximation in the infrared. But then actually the dictionary between the Schwarzschild calculation and the JT gravity calculation is a tautology. It's really the JT gravity and Schwarzschild quantum mechanics are on the nose one and the same thing. There's no difference between this particular prescription that I was giving here. You can be derived from JT gravity, and you can show that it's equivalent to the Schwarzschild quantum mechanics.
Thanks.
From the Hawking quantized, or some rough estimate for that from this computation? Or?
Yeah, actually, indeed, I didn't sort of ask that question, which I can throw into the group. When do we think that this thing starts dominating over that thing? Again, when this distance gets shorter than that distance. So indeed, precisely when I'm here at beta over 8, that's when the thing jumps. At beta over 8 is precisely where this 2 tau becomes less than tau minus tau tilde, and that's where this thing takes over. So there are a couple of questions perhaps you can ask. How good of a model is this thing of a Hawking pair? But I think the following statement is kind of true. So in some sense, I'm doing nothing else than the calculation that Hawking perhaps might have been able to do himself, in the following sense that I'm putting the Hawking pair in there, and then I'm saying, hey, let's take into account the back reaction of the Hawking pair. Initially, people might have said, hey, the Hawking pair was virtual, because if I'm a freely falling, infalling observer, I shouldn't see the Hawking pair. So in that respect, indeed, in this particular regime, where the Hawking pair is still very close to the horizon, I would indeed be saying, hey, you know, if I encounter a Hawking pair too close to the horizon, I probably think that I've made a mistake, because maybe I was secretly accelerating, and the thing that I actually saw was an Unruh pair that I was creating myself. So this, in that respect, I think that explains why this E prime is probably bigger than E, because it's still kind of enforced by the fact that I kind of put the particle there. But at some point, this particle sort of goes on shell. And what's interesting is that this Wick contraction, the way you have to think about this Wick contraction, is precisely because we're doing this other Wick contraction in the C matrices. So what's happening here is the following, is that this thing here is entangled with that. It wants to be entangled with that. And the reason why it wants to be entangled with that is because the number of states in between is very large. I find this a very attractive picture. It basically means that any two things that are correlated and are undergoing a Wick contraction, they're doing that because most of the intermediate states are sitting in between them. So we like communicating with each other because we have many states that we can put in between ourselves. But then at some point, there are going to be more states in the radiation. So this Hawking particle is going to say, hey, you know what? Maybe this is going to be a faraway friend of me, the Hawking partner. So he's losing the memory of his Hawking partner. And he sees all these other particles around himself, which are the external radiation. And at some point he says, hey, you know what? I'm just going to Wick contract with those guys. And this is, by the way, how entanglement always, as soon as I walk in this room, who knows how many things I forget about what I've done here. But so basically you go to a new environment, and then the environment can start dominating what you're going to do, and that's sort of when the information comes out.
More questions? Well, if not, let's thank Herman for the lecture. Oh, there's one. How to embed JT gravity in string theory. Might be able to recover unitary evolution of quantum state in JT-SYK when embedded in string theory instead of an average in an ensemble of theories.
So let me maybe say the following, is that I've been able to draw these pictures in SYK by mapping it to JT gravity, and the idea that there is some kind of bulk interpretation as a black hole. I would say the added value of being able to embed JT gravity and SYK in string theory is that we actually then have a way, and this is the power of ADS-CFT, is that there's an argument that if you have a top-down construction, you can kind of say, what is the weakly coupled description of the D-brane theory, such that if I go to the strongly coupled version of that theory, that there is a dual theory, and that dual theory can also be derived as a given string theory on ADS. So there's going to be a UV description of the bulk, and there's going to be a UV description of the boundary. Do we understand closed string theory completely well enough to call it a UV complete theory? Probably. Okay, we can be agnostic about it. In some sense, the boundary description might maybe the better description, because quantum mechanics is a little bit more manifest there. But nonetheless, we have much more information about what's happening in the bulk if we have a UV, if we have a string theory construction. So I wouldn't necessarily say that having a string theory construction would be immediately, sort of that the immediate gain would be more of the ensemble point of view. Personally, again, I have the same point of view that most of the physics here in the SYK model probably is also present if I just take one value of the couplings rather than doing the disorder averaging. That was just a calculational trick. But obviously it's going to be very interesting. If any one of you has some idea of how to embed SYK or JT gravity in string theory, go for it. Try it.
All right. I think we'll stop here, and there will be more questions in the question session. So
Okay.
Let's thank Herman again. And please don't go before you go to the coffee break. We'll take the picture.